Welcome back, everyone, to another deep dive. This time we're taking on something that might sound a little intimidating at first. Permutations and
Oh
combinations.
yeah,
But trust
yeah.
me,
It does sound a little dry.
it's way more fun and actually incredibly relevant than you might think.
Yeah. It's really about possibilities. Like how many different ways can something happen?
I like that. Okay, so our mission today is to really break down the core concepts of these permutations and combinations, figure out how to tell them apart, which I think is where a lot of people get tripped up, and then most importantly, how can we actually use this stuff in our lives?
Exactly. Yeah. Because it comes up everywhere more than you might think.
Everywhere. More than I might think.
Mm.
Intrigued? Let's start with the basics.
Mhm.
What are we talking about when we say the fundamental principles of counting?
Okay. So there are really two key principles here. The first one's called the multiplication principle.
Multiplication.
And this one says if one event can happen in ways and another can happen in unways, then the total number of ways those two things can happen together is sometimes.
Okay, so let me try to put that in like a concrete example. If I'm trying to decide between 5 different colleges, and each of those colleges offers 10 different majors that I'm interested in,
Perfect.
I multiply 5 times 10 to get 50 different paths that I could choose.
Exactly. Yeah.
Okay, that makes sense.
Yeah.
What about the addition principle? How does that come in?
So the addition principle is more about when you're choosing one thing out of several possibilities.
Okay.
So you're adding the number of ways each event can occur.
So instead of choosing a college and a major, I'm choosing between college or taking a gap year and traveling the world.
That's a good example.
2 totally different paths.
Let's say there's 5 colleges you're considering, and let's say you've come up with 3 different travel itineraries for your gap year. Then using the addition principle, there'd be 5 plus 3 or 8 different options.
Okay. I think I'm with you. So far, so good. These principles seem pretty simple, but I have a feeling they get a lot more complex when you start combining them.
Absolutely. That's where factorials come in.
Factorials.
Yeah.
Yes, I vaguely remember these from math class.
You're going way back.
It's something about multiplying a number by all the whole numbers smaller than it, right?
That's exactly it.
Okay.
Yeah. So 5 factorial, which we write as 5 with an exclamation point, would
Right.
be 5 times 4 times 3 times 2 times 1, which equals 120.
And the exclamation point always used to throw me off.
Yeah, it looks a little scary.
So we're just multiplying a bunch of numbers together?
Yeah.
But why are factorials so important for this whole counting possibilities thing?
Well, factorials show up all the time when we're dealing with permutations and combinations, and they help us calculate the total number of ways to arrange or select things.
Okay.
And here's a fun fact. 0 factorial,
Which is 0.
which is 0 with an exclamation point, is actually equal to 1.
Really?
That might seem counterintuitive.
It does.
But it's a key rule.
Okay. I'm going to have to trust you on that one.
Yeah.
But now we're getting to the part that I think a lot of people get confused about. Are we ready to tackle permutations versus combinations?
Let's do it. This is where people often get tripped up, so let's make sure we really nail it down.
What's the big difference?
Order. In permutations, order matters. In combinations, it doesn't.
Okay, I need a real-world example to really get this. Can you give me one?
Sure. Think about arranging people for a group photo.
Okay.
If you switch the positions of 2 people, you get a totally different photo, right?
Yeah, of course.
That's a permutation. But if you're just choosing a team of players from a larger group, it doesn't matter who you pick first or last. The team is the same. That's a combination.
So if I'm putting together the starting lineup for my fantasy basketball team, the order I choose those players really matters. But if I'm just handing out jerseys to my rec league team,
Exactly.
it doesn't.
Yeah, perfect.
That makes a lot more sense. Okay, so how do we actually express these mathematically?
So for permutations, we use the notation NPR, where N is the total number of objects and R is the number you're selecting or arranging. And for combinations, we use NCR.
So these are like shorthand ways of writing out these calculations.
Yeah. Exactly. They represent the number of possible permutations or combinations. And yes, there are formulas to calculate NPR and NCR, but those are just tools to help us count more efficiently.
Got it. So we've laid the groundwork. Now I'm ready to get my hands dirty with how we can actually apply all this. What's next?
Let's jump into some word problems.
Ooh, word problem.
Yeah, they're like puzzles that'll help us see these concepts in action.
Okay, hit me with a challenging one. I'm ready to put my permutation and combination skills to the test.
All right, I like your attitude. Okay,
Right.
How about this? Imagine you have the word banana.
Okay.
How many different ways can you arrange those letters?
Banana.
Okay.
6 letters.
Yeah.
So my first instinct is to say 6 factorial dollars. which would be 6 times 5 times 4 times 3 times 2 times 1. But then I'm thinking,
Uh-oh.
we have repeating letters in there. We got 3 A's and 2 N's.
Yes,
It's got to change things, right?
You're absolutely right. We need to account for those repetitions. To do that, we divide 6 factorial by the factorials of the number of times each letter repeats.
Okay, so we're dividing 6 factorial by 3 factorials for the A's and 2 factorial for the N's. Let me grab my calculator here. Okay, 6 factorial divided by 3 factorial times 2 factorial is 60. 60 unique ways to arrange the letters in banana. That's a lot less than I initially thought.
Exact. Now let's add a constraint.
Okay.
How many arrangements are there if the vowels must always stay together?
The vowels must always stay together.
So the 3A has become like one unit,
Right.
and then we've got the B and the 2 N's as the other letters.
Because they did.
So to figure that out, we would treat the vowels as one unit and arrange the resulting 4 units. So that gives us 4 factorial.
Exactly.
And then we need to arrange the vowels within their own little group, which is 3 factorial. So 4 factorial times 3 factorial, that's 24 times 6, 144 arrangements where the vowels stick together.
Perfect. See how adding a simple constraint changes the whole picture?
Yeah.
Now imagine we're playing a word game, and we have to figure out the rank of a specific arrangement of banana in a dictionary. Let's say the word is nana-AB. Nana-AB.
Okay.
How would we approach that? So we need to think about all the words that would come before nana alphabetically
Right.
in this imaginary banana dictionary.
Exactly.
So first we consider words starting with A, because
Okay.
that comes before N alphabetically.
Yeah.
And since the vowels have to stick together, any word starting with A is going to have that AAA unit first.
Uh-huh.
So to figure out how many words start with A, we just need to see how many ways we could arrange B and N.
Exactly.
That would be 3 factorials divided by 2 factorials because of the repeating N's. So there are 3 words that come before Nana A,
You got it?
and the Nan AB would be the 4th word in our banana dictionary.
Perfect.
Okay, I'm feeling like a word game master now, but I'm ready to move beyond words. What other scenarios can we explore with this?
Let's switch gears and talk about selecting objects.
Okay.
Imagine we have a box filled with 5 red balls and 6 white balls. You need to select 6 balls in total. How many ways can you do this if you need at least 2 of each color?
Okay, I remember these types of problems. So we need at least 2 red and at least 2 white balls in our final selection of 6.
Yep.
That means we have a few different cases to consider, right?
Exactly. We could have 2 red and 4 white, or 3 red and 3 white, or 4 red and 2 white. We need to calculate each of those cases and then add them all up.
Got it. So for that first case, 2 red and 4 white, how would we calculate that?
Well, we can choose 2 red balls from 5 in 5C 2 ways.
Okay.
And we can choose 4 white balls from 6 in 6C 4 ways. And to get the total combinations for this case, we'll multiply those 2 numbers together.
So 5C, 2 times 6C, 4. 5C2 is 10, and 6C4 is 15. Multiplying those, we get 150 combinations for that first case. Okay, now what about 3 red and 3 white?
Same logic.
Yeah.
We calculate 5C3 to choose the 3 red balls from 5 and 6C3 to choose the 3 white balls from 6.
Okay.
And then we multiply those together.
5C3 is 10, and 6C3 is 20. Multiplying those, we get 200 combinations. And then for our final case, 4 red and 2 white. We do 5C, 4 times 6C2. See, 5C, 4 is 5, and 6C2 is 15. That's 75 combinations.
You're on a roll.
And then to get the total number of ways to select those balls with at least 2 of each color, we add all of those combinations up.
Right.
150 plus 200 plus 75
Exactly.
gives us a grand total of 425 ways
Wow.
to select those balls. So even with a seemingly simple selection problem
Yeah.
like this, there are so many possibilities. And we've only just scratched the surface of what we can do with these permutations and combinations.
Exactly. Are you ready to explore how we can use these concepts to divide people into groups?
Group formations. Okay, I'm game.
Yeah.
Let's say we've got a class of 15 students, and we need to divide them into 3 groups of 5 students each. How many ways can we do that?
This is a classic combination problem. Since the order of students within a group doesn't matter, we'll use combinations. We start by choosing 5 students out of 15 for the first group, which is represented by 15C5.
Okay, and 15C5 gives us, let me check my calculator, 3,003 different ways to form that first group.
Right. But we're not done yet. We've got 10 students left, and we need to choose another group of 5.
So we calculate 10C5.
Exactly.
10C5 is 252. So to get the total number of ways to form all 3 groups, we multiply the number of possibilities for each group. 3,003 times 252 gives us 756,756.
Wow.
Different ways to divide the class.
That's a lot.
Yeah, my brain hurts a little bit thinking about all those different possibilities.
Yeah.
But let's add a twist to this scenario. What if two of the students are best friends and they absolutely have to be in the same group?
Ooh, good one.
How does that change our calculations?
Well, we can't treat them as individual students anymore. It's like they come as a package deal.
Right, so instead of 15 students, we're really working with 13. But how do we make sure that our inseparable duo ends up in a group of 5?
Since they have to be together, let's first form a group of 3 from the remaining students. That would be 13 ways to choose those 3.
So our best friend pair just automatically gets added into that group of 3, making a group of 5.
Exactly. And then we have 10 students left
Right.
to split into 2 groups of 5.
Which we already know is 10C5 or 252.
You got it. So the total number of ways to divide the class with our best friend constraint is 13C3 times 10C5.
Okay, 13C3 is 286. Multiply that by 252 gives us 72,072 ways.
Much more manageable.
It's fascinating how adding one little condition like that can so significantly reduce the number of possibilities.
Constraints can really simplify things.
Okay, I'm ready for a new challenge.
Yeah.
What else can we throw into this mix?
Let's move from lines to circles and talk about circular permutations. Things get a bit more interesting when we arrange objects in a circle instead of a straight line.
Circular permutations. Okay, I've always found those a little bit tricky. Like, how do we even define what a unique arrangement is when everything's in a circle?
Great question. Think about people sitting around a round table. If everyone shifts one seat to the right, it's still considered the same arrangement because their relative positions to each other haven't changed.
Okay, so how do we account for that when we're calculating these circular permutations?
The formula is actually pretty simple. For n distinct objects, the number of circular permutations is n minus 1 factorial.
Okay, so if we have 5 people to arrange around a table, we do 5 minus 1 factorial, which is 4 factorial, or 24 different arrangements.
Exactly.
So it's 1 less factorial than if we were arranging them in a line.
Right. Now let's add a constraint to make things more interesting.
Uh-oh.
Let's say we have 5 boys and 5 girls, and we want to seat them around the table, but no 2 girls can sit next to each other.
Okay, so we need to alternate boys and girls to avoid having 2 girls together.
Exactly. To solve this, we can start by arranging the 5 boys around the table. That would be 5 minus 1 factorial or 4 factorial ways to do that.
And then we have 5 spaces created between the boys where we can put the girls.
Exactly.
And we can arrange the 5 girls in those spaces in 5 factorial ways.
You got it. So using the multiplication principle, the total number of arrangements is 4 factorial times 5 factorial, which is 24 times 120.
A total of 2,880 possible arrangements.
That's a lot of seating charts.
Yeah, it's amazing how strategic we have to get with these constraints.
Oh.
Okay, so we've done word problem selections, group formations, and even these circular arrangements. What other surprises does this world of permutations and combinations have for us?
Let's take a quick detour into the realm of number theory and see how these concepts connect to divisors.
Divisors. So like for the number 12, the divisors are 1, 2, 3, 4, 6, and 12. I never would have guessed that divisors have anything to do with permutations and combinations.
It all comes down to prime factorization. Let's take the number 360 as an example. Its prime factorization is 2 cubed times 3 squared times 5 to the first power. To make a divisor of 360, we can choose any power of 2 from 0 to 3, any power of 3 from 0 to 2, and any power of 5 from 0 to 1.
So it's kind of like we're making choices.
Exactly.
We have 4 choices for the power of 2, 3 choices for the power of 3, and 2 choices for the power of 5, and then we multiply those together.
Exactly. The total number of divisors of 360 is 4 times 3 times 2, which equals 24. It's a really cool way to use combinations to find the number of divisors of a number.
That's such a neat trick. Okay, are you ready for one final mind-bending concept before we wrap up?
Let's talk about derangements.
Derangements, okay. The word itself sounds kind of mysterious. What are we talking about here?
Imagine you have like n letters and n corresponding envelopes. A derangement is an arrangement where none of the letters end up in their correct envelope.
It's like accidentally mixing up everyone's mail on purpose.
Exactly. It might sound a little strange, but there's actually a formula to calculate the number of possible derangements for any given science.
So for example, if you had 4 letters and 4 envelopes, there would be 9 possible derangements.
Exactly. It's kind of surprising that even with these constraints, we can still figure out how many different ways it can happen.
That's amazing. We've covered so much ground today, from basic principles to these mind-bending derangements. I never thought counting possibilities could be this interesting.
It's all about looking for patterns and finding the right tools to solve the puzzle.
So to all our listeners out there, the next time you're faced with a situation where you need to count possibilities, remember the power of permutations and combinations.
Yeah.
It just might be the key to unlocking a solution.
And remember, sometimes it's not about finding the one right answer, but about exploring all the different possibilities that are out there.
That's a great point. Thanks for joining us on this deep dive into the world of permutations and combinations. Until next time, keep those minds curious.